move on. Now, this is a description, a sort of visual symbolization of what differentiation is. It's saying, okay, from the chicken, if you differentiate the chicken, there comes an egg, the change in chicken, and then if you anti-differentiate the egg, you should get back a chicken. Now, that's not exactly the case, because in reality, you would probably get something more like the chicken plus C, which we're going to look at soon. Which is basically saying if you differentiate the chicken, and there's also a constant next to the chicken, it's an interesting metaphor, then when you differentiate that, this constant will disappear, which means that when you anti-differentiate, you have to add the constant again, but you don't know what it is, so you just put plus C, the common constant value. So we'll look at that soon. So the common notation for anti-differentiation is this symbol here. You have this symbol here. Then you have some sort of function. So that's function x here. And then you have dx on the end, which is saying the difference. So with this, you can often not actually have this dx in here, the difference in x. You can not have it in there. And with your working, you often won't write it every time. But if you were to write it in a proper way, it's good to have that dx in there generally. The notation for definite integration, which means basically you think about it like you're integrating between 2 points on a line, then it's very similar. So you have this same anti-differentiation, this integral symbolization, and then what you have is B and A. And that is A is the start point that you're looking at, and B is the end point. So what you're doing when you're doing definite integration is you're integrating between 2 points, and you'll understand what that actually means soon. What values does that give us? So what are indefinite and definite integrals? So the indefinite integral of f(x) is the function that gives us the original equation if f(x) is representing the gradient. So basically, if f(x), let's say gx is equal to x squared, then if we were to differentiate that, so we had g differential of gx is equal to fx, let's say, so that's fx is the differential of gx, that would be equal to 2x, right? So then basically the integral of fx is then equal to gx. And that's sort of what it is. You're just reversing the process that you did. The only difference is it would actually be equal to gx plus c, because gx could have, you could add plus 2 on the end, or plus anything on the end. Like you could add plus c on the end. As long as c is a constant value, then that value would have disappeared when you differentiated. So you have to add the plus c on the end again, and this time it could represent any value. And we'll look at that again in a second if that doesn't make any sense to you. So definite integrals, on the other hand, is not a function. We're not getting a function out of it. We're getting a number. We're getting a number that represents the area under the curve of fx from x equals a to x equals b. So let's say we have this line here, and this is a curve we have. Whoa, this is bugging out. Let's say this is a curve we have. Now, if we want to get the area underneath here, let's say we want to get the area underneath here, actually. Let's cut off and let's get the area in this spot here. Now, if this is A and this is B, and let's call this fx. There you go. Now, if this is A and this is B, this will get us the constant value that is the area underneath the curve between A and B. So there's a little description of why that occurs later. Bit hard to wrap your head around, and not necessary really to wrap your head around in reality. But if you're an enjoyer of mathematical theory, maybe you want to look into it, why that actually is the case. But what you need to know to pass these tests and pass your assignments is to understand what you can actually do with it, as opposed to why it is how it is. So we're going to look at derivatives. So to understand antiderivatives. So if we derive x squared, that will result in 2x. If we derive x squared plus c, that will also result in 2x because we're assuming here c is a constant value. It's not a variable. So c is any constant value that will become 2x. And you can see that here, there's that extra 1, and that disappears. Here is pi, that disappears. Now, just a little recap, if we were to derive, let's say 2x cubed, that would become 3 times 2x squared. So basically, you really should be pretty comfortable with these general rules to quickly derive things. Because they're very useful, and they will also be useful in anti-differentiating and understanding. Basically, you'll get a result when you do anti-differentiation, and then you're going to look at the result and be able to consider, is this result correct? So if you understand these general rules that we have to go through, I think some rules are on your formula sheet, then you will be able to apply those. So, yep. So what is the antiderivative of 2x? Well, we know that x squared plus 1, x squared plus pi, x squared plus anything always results in a derivative of 2x. It doesn't matter what this constant value is on the end, it's 2x. So if we anti-derive 2x, if we do the if we anti-differentiate, 2x, we have to get this plus c, because this plus c represents the possibility of it being pi, of it being 1, of it being 0. It represents the possibility of there's any possible constant value, and that's the case. So, yep. So this is sort of a general rule for finding the anti-differentiation. If all you had was if you were finding the anti-differentiation of x to the power of n, of to the power of anything, and if that's all that was in there, you can utilize this formula here, and we'll prove that in a second. So let's say we just have xn, that would be equal to 1 over n plus 1, given this formula, xn plus 1 plus c. So in that scenario, we could then prove this by then deriving this. So let's get the, let's say this equals fx. Now let's get the differentiation of fx. So that would be equal to, so we have this constant value at the front still, because n is a constant value as well. Now we multiply that by our answer. So our answer will be in brackets n minus 1, because let's say it's x3. If we derive that, it would become x2 times 3. So we have times n minus 1. That's this value up here is now thrown out the front. And then times x n plus 1 minus 1. So the power goes down when we derive. Plus c? Nope. We don't have the plus c because it's just a constant value. So if it's a constant value that's sitting there on its own, we get rid of it because the power keeps moving down, and that's sort of a constant value outside of x to the power of 0. So c can always be considered. You can consider it like c times x to the power of 0. So then if anything's to the power of 0, then the next step is we remove it. So if that confuses you, just ignore it. Just think a constant value disappears when we derive. So then we can expand this. We have, this should be n plus 1. We have n plus 1 over n plus 1 times x, n equals xn. So that's just a little proof of, okay, this rule leads to this, and if we derive this, it leads back to our initial value that we initially integrated, just to prove that this is true, that the anti-differentiation of xn is equal to 1 over n plus 1 multiplied by x to the power of n plus 1 plus c. So let's actually work with this as an example. We want to find y. So when we want to find y, it's sort of like saying we want to find fx, because usually when you say fx equals etc., you would have it so y is equal to etc. Y is equal to fx. So this is our derivative. That's what it's saying here. Our derivative of an initial value is this. So now we want to get the anti-differentiated value of this. If we follow this formula, that would be equal to 1 over, so n here is 1, because this is to the power of 1, so 1 plus 1, multiplied by x, 1 plus 1, multiplied by, we have this constant value at the front, 3. Now we do have a plus c, but we also have this 2 here. Now this 2 also is its own term. So we also have to sort of anti-differentiate it separately. So we also have a plus 2, or sorry, a plus 1 over 2. I'm making a mistake. Plus 1 over 1 times x, 0 plus 1. So this culminates in 1 over 2 x squared times 3 plus this should have a 2 at the front, plus 2x plus c equals 3 over 2 x squared plus 2x plus c. Now it's my opinion that and it's up to you what you choose to do, but it's my opinion that applying this formula up here leads to very large expressions like this, which I would say to me is undesirable. I think it's better if you sort of get used to being able to just look at it and feel it out. So okay, so there's one of the terms in here is 3x. So okay, what could be derived to make 3x? That would be my question. I know that there must be an x squared, factually, based on the fact that if x squared is derived, it becomes x, and that's the only thing that will become x if it's derived. So I know there must be an x squared. Now, if we did derive x squared, it would become 2x, but we want 3x instead. So we're probably going to have to put a 3 over 2 out the front here, so that it becomes 2x times 3 over 2, which is equal to 3x. So this is sort of useful to get used to these patterns. If you can't, I know some students, it's just not really their way of learning, getting used to just like intuiting how to turn 3x, like what creates 3x, sorry, if you derive. So this is a useful formula if you're one of those students that likes to basically rely on formulas to an extent, which is more reliable. And so I definitely think it's sort of up to you what you prefer. Now, one note is something that might help you a little bit is that if we have the differential of 3x plus 2, it is the same as the differential of the anti-differentiation, keep making that mistake, the anti-differentiation of 3x plus the anti-differentiation of 2. So that might make this formula a little bit easier since they're the same. So you basically apply this formula twice, as I did down here. You apply this formula twice because you are anti-differentiating both of these terms separately. And then each one of them would have their own c, I guess, but that just culminates in one c because c is any constant value. So any two c's lead to one constant value because they can add together.